so long ago, astronomers thought they were getting close to understanding what the universe is made of. First, there's matter, which makes up the stars and galaxies that light up our night sky. Then, there's dark matter. It's thought to be an unidentified type of particle that gives off no light. But we know it exists because of its gravitational pull. Only recently have astronomers discovered that there's a third presence in our universe, and it's not any type of matter at all. It's a mysterious phenomenon that could literally be caused by empty space.
It's called dark energy, and its growing influence in the universe is so important it will dictate the ultimate fate of everything else. The only trouble is cosmologists aren't sure what dark energy is, and finding out has become one of the greatest scientific quests of our time.
The seeds of the quest were planted nearly a century ago. That's when astronomers first became aware that the tiny blobs and swirls of light they could see in their telescopes were galaxies. Galaxies are vast systems of stars, like our own Milky Way, but far off in the cosmic distance. Here, the Hubble Space Telescope peers across the edge of the Milky Way toward the constellation Centaurus to reveal the spiral galaxy M83. Compared to other galaxies, M83 is a close neighbor to the Milky Way, just 15 million light-years away. But this entire system is rapidly moving away from us at the rate of over 500 kilometers every second. Much farther off in space, there are countless more galaxies that are doing the same thing. Here, the Hubble telescope explores a giant elliptical galaxy surrounded by a swarm of smaller neighbors. This cluster of galaxies is more than 30 times farther away from us than M83, and it's receding at more than 10,000 kilometers per second. No matter where we look in the universe, astronomers have found that the farther a galaxy is from us, the faster it's moving away. In the 1920s, it was astronomer Edwin Hubble who first grasped the meaning of this relationship. Hubble realized that all the galaxies must be spreading apart from each other, which makes more distant galaxies appear to recede more quickly. The discovery led to a mind-blowing conclusion. Our universe is not static, but expanding outward in all directions. And as space expands, it's taking the galaxies with it. An expanding universe is a strange idea to come to grips with, but it makes sense. If the universe were static, gravity would have pulled all the galaxies together by now. The expansion explains why this hasn't happened, but it also leads to another powerful conclusion. Because space is growing, it must have been smaller in the past. At some point, the entire universe we can see today was confined in a volume of space smaller than an atom. To have so much matter and energy contained in such a tiny region is unimaginable. But it's this situation that led to the Big Bang. The fiery birth of the universe. Having discovered the Big Bang, astronomers realized they could determine when it happened simply by measuring the rate at which the galaxies are flying apart, and then working backwards. To measure the expansion, astronomers need to look at several galaxies and compare two things: distance and speed. Speed is the easy part. When objects are moving, the light they give off shifts in frequency in direct proportion to speed. This is called the Doppler effect. Here on Earth, it's used to measure the velocity of approaching storms, and it's the principle behind police radar. Measuring the distance to a galaxy is a much tougher problem, and for most of the 20th century, doing it with accuracy was beyond the ability of even the biggest telescopes. That would change when the Hubble Space Telescope was launched. Giving astronomers a new and better view of the galaxies. But what they didn't know then is that it would also provide the first clue to the existence of dark energy. By the 1990s, astronomers knew the Hubble Space Telescope was their key to measuring the age of the universe. Freed from the distorting effects of Earth's atmosphere, the Hubble had the power to peer into nearby galaxies and for the first time see individual stars within those galaxies. But astronomers weren't just looking for stars in general. They were hoping to spot Cepheid variables. Cepheid variables are extremely useful because they pulse with a regular cycle, and the brighter they shine, the slower they pulse. So just by timing a Cepheid's pulsations, astronomers can tell how much light it's giving off, and therefore how far away it must be. Starting in 1993, a team of astronomers used the Hubble to hunt for Cepheid variables hidden in nearby galaxies. And they found plenty. The Cepheids gave them a way to measure the distance to each galaxy. Meanwhile, by using the Doppler shift, astronomers could directly measure how fast those same galaxies are receding from us as the universe expands. The final step is just arithmetic. For each galaxy, the speed divided by the distance is the expansion rate of the universe. The more galaxies are measured, the more confident the result. And by knowing how fast the universe is expanding, astronomers could then work out when it all began. It was one of the Hubble's most important results. But when the answer began to emerge in 1994, astronomers were puzzled. Their calculations showed that the universe was less than 12 billion years old. That was younger than earlier estimates, and it didn't match well with some other evidence. Evidence that included white dwarf stars, tiny stellar relics no bigger than Earth that are left over when stars like our Sun burn themselves out. Some of the oldest white dwarf stars can be found inside globular clusters. These are vast, spherical swarms of stars that date back to the formation of our galaxy. Because white dwarf stars cool as time passes, astronomers can look for the coolest, dimmest white dwarfs in a cluster and use them to measure the cluster's age.
But here's the problem. The oldest white dwarfs seem to be more than 12 billion years old. That would make them older than the universe, which doesn't make sense. Somehow, somewhere, astronomers were missing a key piece of information.
In 1998, the missing piece finally turned up, and it changed everything. It involved another way of measuring the distances to the galaxies. This method is based on a particular type of exploding star, which can be seen from a much greater distance than a Cepheid variable. The explosion involves two stars in orbit around each other. One is a tiny white dwarf, the other a massive red giant. In this scenario, hot gas escaping from the giant star is pulled by gravity onto the white dwarf companion. Eventually, so much matter falls onto the white dwarf that it becomes unstable. This triggers a thermonuclear explosion, and the white dwarf goes supernova. What is crucial for astronomers is that the trigger point for the explosion is always the same. And so supernovas of this type always shine at about the same peak brightness. And just as with Cepheid variables, knowing the true brightness of something means knowing its distance. But supernovas can be spotted in galaxies that are even farther away, and their light is reaching us from a more remote time in the past. So by measuring the distance to these far-off supernovas and their host galaxies, astronomers could check to see if the expansion of the universe has changed over time. They were expecting to find the expansion gradually slowing down. That's because the gravity of all the matter and dark matter in the universe acts like a brake pedal on cosmic expansion. The more matter, the more gravity, and the more gravity, the harder it is for things to fly apart. But remarkably, they found the opposite. The expansion of the universe appears to be speeding up. This surprise discovery explains the contradiction over the age of the universe. If space is expanding at a faster rate now than in the past, then it must have taken longer for the universe to reach its current size. That would make the age of the universe greater than 12 billion years. The latest estimate puts it at 13.8 billion years old, which is older than any known star. But if the universe is accelerating, what's causing it? Just like dark matter, there was no way to observe this new phenomenon directly. So cosmologists called it dark energy. Follow-up observations soon confirmed and strengthened the case for dark energy. And by 2011, 3 astronomers involved in the initial find, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize. With the discovery of dark energy, the universe had become a more interesting and more mysterious place. Now it was up to cosmologists to understand what an accelerating universe meant for their theories. And for us. cosmologists were given a new way to see dark energy's role in the universe. It was WMAP, an orbiting spacecraft designed to map the cosmic microwave background. The background is a form of relic light that was emitted a few 100,000 years after the Big Bang, when the universe was still white hot. Because of the Doppler shift, this signal is no longer visible to the eye, but it can be detected in the microwave part of the spectrum. One of the signal's key features is that it contains tiny fluctuations that WMAP saw as speckles across the microwave sky. This turned out to be incredibly handy for cosmologists, because the average size of those speckles is related to the total amount of matter and energy in the universe. The data reveal that total is far greater than all the galaxies combined. In fact, all the matter we can see only adds up to a 5% slice of the cosmic pie. But the galaxies are embedded within vast concentrations of dark matter that add up to much more. Altogether, dark matter contributes another 27% to the pie. That still leaves more than 2/3 of the contents of the universe unaccounted for. It's this missing share that cosmologists now say is taken up by dark energy, the mysterious entity that is causing the expansion of the universe to speed up. But to understand what this really means for the universe, we need to know what dark energy is. One possible answer has already been around for about a century. It's called the cosmological constant. It's a mathematical term that Albert Einstein added to his theory of general relativity in order to counterbalance gravity. Einstein used it to explain why all the matter in the universe hadn't converged in one place. But once astronomers discovered the universe was expanding, Einstein realized he didn't need the cosmological constant after all. He even called it his biggest blunder. But with the discovery of dark energy, the cosmological constant was back on the table. The idea is that space has its own built-in energy, and that this energy has a repulsive effect. As the universe expands, more space leads to more repulsion, so the expansion speeds up like a runaway train. So far, the observations agree with this idea, but there are other theories too. For example, it could be that dark energy is the result of a previously undiscovered force of nature. If so, its influence might gradually weaken over time. Or there could be a more chilling possibility. Rather than a constant, the acceleration of the universe could itself be accelerated. In that case, it will eventually overtake all other forces, pulling apart individual galaxies, stars, and finally atoms. Cosmologists call this scenario the Big Rip. To help distinguish between these possibilities, a US-led team of scientists has launched the Dark Energy Survey. This project uses a special camera installed on a telescope in Chile that can look for evidence of dark energy in a number of ways. One of the ways involves probing the large-scale structure of the universe. This structure looks like a cosmic spider web, with all the galaxies concentrated in enormous strands that separate empty voids millions of light years across. If measured carefully, the regular spacing of these strands can be used like a giant ruler to measure how the expansion of space has changed over time. The Dark Energy Survey began in late 2013. To help pin down dark energy, scientists hope to measure as many as 300 million galaxies over a 5-year period. Meanwhile, in Canada, astronomers have realized that they can do with radio waves what the dark energy camera does with light. Their project involves a series of trough-like radio antennas, each one 100 meters long. The troughs are used to map the distribution of distant clouds of intergalactic hydrogen, which pass overhead as the Earth turns. The advantage of this method is that the hydrogen clouds are easier to detect than individual galaxies, so astronomers can use them to peer back to earlier times in cosmic history, when it might be easier to distinguish between rival theories of dark energy. Looking further ahead, the European Space Agency has proposed a space telescope named Euclid that is specially designed for the task of measuring dark energy. It could launch as early as 2020. And NASA is pursuing a dark energy telescope of its own, called WFIRST, currently set to launch in 2024.
20 years ago, no one knew dark energy existed. Now, understanding it has become our cosmic priority. And there's something very appropriate about that.
Billions of years ago, any civilizations that were around may not have discovered dark energy because the acceleration of the universe was still too small to notice at that time. And trillions of years from now, future civilizations won't see it either. By then, space will be growing so fast that light from the cosmic background, along with most of the galaxies, won't be able to cross it. As those galaxies disappear over the cosmic horizon, they'll take the evidence for dark energy along with them. This is perhaps the greatest revelation of all. Not only is there much more to understand about the universe than astronomers once thought, it appears that understanding is a limited time offer.